So welcome to Math 25, the second class of week 8. And this is an exciting class because we're probably going to finish up all the new material. The homework question is the turn-in homework number 9, and a discount is a percent change. So we need the change and the original. So how much did the price change by? And then, which is the original?
$75.
So we get about 0.09. And we can ask, does that seem like a reasonable answer? And if we had 10% off, that would be $27.50, which would be a little more than we wanted. So 9%, yeah, that seems reasonable. Any other homework questions? I don't know if we looked at the charge ones last time, but it's just finishing one of these enormous tables. So saving for retirement has had a due date, but nothing in this business finance has a due date yet, nor will it, since we just had a question on the margin markup and pricing.
So are we open for questions in the charge option?
Sure.
Talk about number 9.
Number 9. What percentage of his first month's payment was interest? Okay. So we actually, that's a good one for you to pick because we don't need all of the previous stuff going on. Why did it grab that? Okay, so there's his first month. We don't need to find any of the numbers because it gave them to us. Number 10 is just the same, but it asks you to do it with his 10th month using the numbers that you found earlier. but you can do this one without having to do that earlier preparation. So what percentage of the first month's payment was interest? So we have a few numbers. We have all those things. So if we're asking about a percent sentence, then our general Mad Libs formula is something is some percent of something else. The percent is always easy to find. This one was the part. If this one was the whole, or this one is the new, if this one is the old, or this one is the change, if this one is the original, all of that ring a bell? So with all of the numbers there, then what goes in my blanks for this particular problem?
$13.59.
So that's the amount of interest, or that's the amount that the interest is due on. So I don't think we want that one actually.
Is it the ending, the 1386?
No, we want the first month's payment, and we want the interest. Those are the two numbers we care about. So here's the interest,
So
and here's the first month payment.
140. Yeah. 140.
No, the whole, the big one is going to be over here, and the part is going to be over here. And the percent is the thing we don't know. Does it make sense now that you see it? This amount of interest is what percent of the whole payment. So there were two ways to do these. We could translate them, or we could do a proportion. So I'm going to grab that and give myself more room on the screen so I can do them both ways. So, oops, we could ask, about translating it. So a number stays a number. Is becomes equals. What is the thing we don't know? Of becomes multiply. And a number stays a number. Notice we didn't do anything with the percent symbol, so we'll have to deal with that eventually, but not yet. Okay, something is stuck onto y with a times 140, so the opposite is divided by 140. So we get about 0.19. If you like the translate method, you're done. You don't have to do it the other way. If you liked the proportion method, then you set up the percent on one side. In this case, the percent is the thing we don't know, how much out of a 100. On the other side, there's going to be something that comes after the word of. And that goes on the bottom on the other side. And then the last number we haven't dealt with goes in the last space. Then when we cross multiply, solve for y. Now a different thing happens. In this case, we needed replop because it asked for a percent, and we hadn't done anything yet that involved percentages. In this case, there's no replop. The proportion method never uses that. You already have percent over 100 as percent format, so you don't need to do anything else to make a percent format happen. So we can just put a percent symbol on the end. Okay, moving on. So we're in the last topic. We've done markup and margin and pricing and charge options. We talked about the fair spinner games, but I don't want to review them now. They will come back and be part of what we do when we get to weighted average. But let's just start with probability and odds. So probability is a ratio. It's how many outcomes we care about compared to how many outcomes there are total. Okay. So if I want the probability of rolling a 7, actually before I write anything, no, I'll be fine. Okay. Then how many outcomes are a 7? 1, 2, 3, 4, 5, 6. How many are there total? I have 6 times 6 is 36. We often take probabilities and turn them into percents. So 1/6 is one that hopefully you've memorized. You could round it, doesn't really matter. We could take the same picture there we go, and find the probability of rolling a 9, a 10. I mean, that's the one that's highlighted. If you add up 2 dice and roll a 10, so 3 ways you can get a 10. There's still 6 times 6 is 36 ways total. Okay, so that's not bad. There's really nothing new. We already have talked about fractions and how to turn fractions into decimals and how to turn decimals into percents. So now there's just a little extra bit of bookkeeping that whatever the situation is, you have to count how many of the outcomes are ones we care about for this problem. And we also have to count how many outcomes are there total for all the possible situations in the problem. Questions about that? No, everyone's quiet. Okay. Hopefully we're okay. I'm not sure about if it's microphone issues or so dice you might just be familiar with. Here's something that's also easy. The table is made out for you, so you don't have to draw it yourself, but it's not quite so familiar and experienced. There's a gumball machine that has equal amounts of red and green and blue, and someone is going to go and get 3 gumballs out of the gumball machine. So this top square says first they get a red, second they get a red, third they get a red. Then the next square, first they get a red, second they get a red, third they get a green, and so on. And all the combinations are here. There's 27. 9 times 3 is 27. So we could ask a question like, if you do get 3 gumballs, how likely is it to get at least 1 blue? So we need to find all the ones that have at least 1 blue. So 1, maybe I should even put numbers. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19. So we had 19 with at least 1 blue. We had 27 total. So it's about 0.7. Do you want me to go back a little bit, Donna, because you're disconnected?
Yes, thank you. I lost my internet somehow.
Okay. So did you have questions about the two dice sum examples?
Yes.
Okay, so I'll go back and review. The probability is a fraction, a ratio, and it's how many things in the situation we are talking about, like sum up to 7, that's on top, and then how many things total can happen. So rolling 2 dice for a 7, there were 6 ways to get that. And the whole chart is 6 times 6 different possible ways to roll 2 dice. And once we count that, that's the only new thing, because we're just taking a fraction, top divided by bottom to make it a decimal, and then ripple up to make it a percent.
That helps. I couldn't figure out where because I wasn't figuring out where that.
The second example problem was very much the same, except the ones we cared about, instead of the summing of 7 with 6 possibilities, was summing up to 10 with only 3 possibilities. But everything else is the same.
Thank you.
The third example was that somebody is going to get 3 gumballs. And this chart has, for example, first I get a green, then I get a red, then I get another green. So all the combinations of how to get 3 gumballs out. And they wanted to know, will I get at least 1 blue? So we highlight all the ones that had at least 1 blue in them. And there were 19 of those. So the ones we care about for this problem, there's 19. And then it says there's 27, which is just 3 times 9. And again, top divided by bottom, riplop. Just old math after we do a bunch of counting.
So it's not as scary as it seems.
No, it only gets confusing because now there's a very similar, actually let me make this narrow so it copies better. A very similar thing called odds. So the only hard part is keeping these straight. So let's go back to the rolling a 7. So we're again going to make a fraction, a ratio, but now it's not desirable over total like it was for probability. It's desirable over undesirable. So it's still true that there's 6 ways to make a sum of 7 when you roll 2 dice. But I'm not going to put 36 on the bottom anymore. It's not the total that goes here. Instead, it's all the ones that we didn't just count. So I have to take the 36 total, subtract away the 6 that were the ones we wanted, say the bottom is now 30. We could change it into a percent just like before, but we actually don't. Instead, the tradition with odds is to leave it as a ratio and say 6 to 30. And sometimes we'll reduce it. We can divide top and bottom by 6 and say 1 to 5. We could also rate this, especially if you're betting on horses or taking an SAT test, as 1 to 5, or even using the words 1 to 5. So this is a pain in a few reasons. First, just sloppy English language. People will sometimes use probability and odds as if they mean the same thing, and they don't. They are both about a ratio, but the denominator is different. Is it the total for probability, or is it total minus the ones we care about for odds? And then it's also kind of funky that for probability, we always want a percent. That's by far the most traditional way to present the answer. But in odds, we never want a percent. We want either the reduced or unreduced plain ratio. Whether we reduce it is sort of a context thing. We lose the real life information. So it might be simpler to think 1 to 5. We will get a 7 once for every 5 times we don't get a 7. But if you were, whatever, betting on horses, you might want to know actually how many races the horse has run. If it's a brand new but promising racehorse, that might be a different thing to bet on than an old reliable one that has been around for years and won dozens of races. So sometimes the actual count from a real life situation matters, and other times we'll just reduce it and say good enough. Okay, let's go back and do this one with odds too. Oh, I have to copy it above. So it is still true that when we went through and counted them, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19 ways to get at least one blue. But now we're not going to put all 27 in the bottom. Instead, we're going to say 27 total minus those 19 is going to be 8 that are the undesirable outcomes. And we can't reduce this, so we're just done. 19 to 8. Let's look at some homework problems. So the random problems are going to give you a blank chart because we're not sure it's 7s and 10s anymore. And then they're going to ask you about, oops, that should say write your answer, not write you answer. They're going to ask you for the same situation, but once with the probability and once with the odds.
If you also Friday off, we could just let the Alliance know we've been furloughed on Fridays. Carry on.
The probability will have desirable over total, and the odds will have desirable over undesirable. Okay, help me out. What numbers go on top and bottom? Let's start with probability.
Four.
So we're looking for 9 or more. So
9.
this works. Those work. So those are the ones we're counting.
10.
1, 2, 3, 4, 5, 6, 7, 8, 9, 10. It's still true. There's 6 times 6 is 36 total. How about for the odd side? It's still going to be 10 that we highlight.
26.
26, right? 36 minus 10. So this might be done. Or if we want, we could reduce, divide top and bottom by 2. For this one, we should make it a percentage. Okay, and that's all there is to it. It's mostly just counting and then having in your notes the expectations about how to write your answer. In the take-home problems, then we give you a few different things. The even numbers, 8 or more, but very, very similar. Okay, so I'm going to leave this on random problems, but go back to our topics. So that was probability and odds. A similar thing where we have different ways to describe the same situation is absolute change and relative change. I've written this all out. I think I will just narrate this. So this is a trickier thing. It's not harder. It's just, again, the language makes it tricky. The similarness of the two situations makes it tricky. So imagine there's a medicine that can reduce somebody's cancer risk from 44 cases among 10,000 people down to 11 among 10,000. But the medicine does have some bad side effects. You don't want to take it unless you are sure it would be helpful. Is it worth taking it? So normally, if we want to compare two amounts, Timothy has 50 apples in his garage. Donna has 40 apples in her garage. How many more does Timothy have? You subtract things. So we could use subtraction. That's a completely valid way to say which thing is bigger. The old risk was 0.44%. That's 44 divided by 10,000. The new risk is 0.11%. That's 11 divided by 10,000. So we'll take those two risks and subtract them, just like how many apples would be in your garage. So 0.44% minus 0.11% is 0.33%. So in this case, it doesn't sound like much of a reduction, 1/3%. The reason that's so small is we're counting all the healthy people. Since the chance of getting this type of cancer is so small anyway, less than 0.5%, then if we change it, we're not going to get a bigger thing. If we're starting with a small number and subtracting, of course, we're going to get a small number. There's also a relative change. Remember that we started class saying that a percent change is change divided by original. So that's another way to talk about change. Now we have Timothy had 50 apples in his garage. He gave 40 of them to Donna. What percentage did he give to Donna? So change divided by original. There's nothing wrong with that. That's a completely normal way in math to talk about how much things have changed. So we again say that we'll do the change. We just found the change. That was the 0.33 divided by the original. And now we get a big number comparatively, 0.75, 75%. So we could say the medication has a relative change of 75%. And that makes it sound like it's a very effective medicine. The reason this number is big is we're only talking in this case about the people destined to get cancer. Everyone in this equation was part of either the 44 or the 11. All of the almost 10,000 healthy people that were part of this example are no longer present in the second example. So if you are someone that is going to get cancer, then the medicine helps you a lot. If you're someone in the general population, then it's only 1/3% chance that this might actually help you. Probably not worth the side effects. There's also a phrase as likely. So we could have the ratio of the new risk to the old risk and get something called as likely, which again is a pretty big number because we're talking only about people that have the cancer. So if we look on the random problems, then there aren't any of those. And if we look on the turn-in problems, then there's a set of them talking about another medicine. But if you don't get this done, or if we have to do it in class next week together, then that's okay. It's not going to show up on the test from the random problems. The main point of this is just to be aware when people give you changes of small numbers that there's 3 completely valid mathematical ways to talk about how things change. Subtract them, percent change, or 1 divided by the other as a ratio. And when the numbers are all tiny, which one you pick is a big publicity stunt, because you can make something seem like, oh, my answer is tiny, or you can make something seem, oh, my answer is huge. This will save your life. So as we go through life, reading newspapers, pay attention to that kind of thing. Small numbers have issues. So try that in the turn-in problems over the weekend, but don't spend too much time on it. If you spent 20 or 30 minutes on that set, then good enough. We can always do them in class next week. Okay, our last thing is weighted average. So very bottom, congratulations on making it to the end. We've talked about 2 kinds of averages, mean and median. And for both mean and median, everything that was in our sample was equally important. We were looking at houses in the neighborhood and what's the average housing price, or weights of people in a preschool classroom and what's the average weight. And if something was less typical or less representative, like the millionaire builds a mansion in the neighborhood, or someone's income is vastly higher than everyone else's, then that was the job for the median. By finding the middle value of the sorted list, we could avoid something that was atypically too small or too big. But that was a bit drastic. We could either include everything completely equally and find the mean, or we could completely toss out the things that were not very representative and ignore them. There must be some compromise, some way to say that we'll include everybody, but some things count more than others. Some things we recognize are more representative than others. So that's the job of a weighted average. So to find a weighted average, then you're going to make a table. How this works is you list out all the possible ways that something can happen. So in this case, we could roll a 2, a 3, a 4, a 5, and so on. Then the next column, we put a number to it. In this case, the first column was numbers. not always. Maybe we're talking about the popularity of different books or something like that, and it's not a number in the first column. So to do math, we need a number. We'll talk about this a little more as we see some different cases. Then for each possible outcome, we need to know the probability. So how do you get a 2? Well, there's only one way out of 36. How do we get a 3? There were 2 ways out of 36, and so on. So this is a whole bunch of problems, just like we did at the beginning of the class. And then we multiply this column and that column. 2 times 1 out of 36 is 2 out of 36. 3 times 2 out of 36 is 6 out of 36, and so on. And if you wanted to make these percentages, then you could. It would just mean that these aren't fractions either. So if you like percentages, turn all of these into percentages. Then when you're done, you add up that last column, and your answer is called the weighted average. So we've just proved what we have been told all our lives, that 7 is the average thing when you roll 2 dice and add them together. It is not only the most common thing, that was back over here, but if you rolled the dice hundreds and hundreds of times, then 7 would be the average amount you came up with. Okay, so let's go back to one that we don't know the answer to. We all knew already that the average of 2 dice is 7, probably. So we have the 3 gumballs. So every time our kid goes to the grocery store, then he gets 3 pennies and puts them in the gumball machine, because this is long ago when gumball machines used pennies. He wants a blue gumball, and he'll spend up to 3 cents trying to get one. But once he gets one, he stops. So what's the average number of pennies he spends? So we need these categories, these columns. So we have the outcome. We have a value for that outcome. We have the probability. And then we have multiplying to get the product. So in this case, he might get a blue on his first try. Or he might get a blue on his second try. Or he might get a blue on his third try. Or he might be sad because he never gets a blue. Everyone okay with my 4 possible outcomes?
Yes.
Okay, what are the values for these? If he gets blue on his first try, that is 1 cent.
is the, how many chance, right?
Your mic cut out. Something about chances. So if he got lucky and he put 1 penny in and got his blue and stopped, then that would only cost him 1 cent. If it didn't happen, he would keep going. So now he spent 2 cents. And if he gets his blue, he'll stop. He'll save his penny for next time. If he still hasn't gotten a blue, he's going to try again. If he never gets a blue, what number goes here?
Three.
It's still 3 cents, right? He only has 3 pennies. So once he spends all 3 of his pennies, he's out of luck if he hasn't gotten the blue. Okay, so how many times can you get a blue on your first try? So 1, 2, 3, 4, 5, 6, 7, 8, 9. If you wanted to make a probability into a percentage, you could. Or if you wanted to write it as a decimal, you could. Either way works. Okay, how many ways can you get a blue the second try? So that would be this one, or that 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 one. Does that make sense? We're not counting these because they've already been part of this situation. If I wanted to be very technical, I could say blue second try, but not first. So 1, 2, 3, 4, 5, 6. How many ways could you get a blue only on the third try? So again, what I'm really thinking is but not first or second. So that would be that one, and that one, and that one, and that one. Right, third one is blue. And then how many ways could he never get a blue? That's these 4, 5, 6, 7, 8. Okay, I'm going to slide that over just a little bit. So I don't want to clutter this up and confuse people. If you want to multiply and have fraction math, you can. So let's pretend that you're a fraction person, and we'll use a different slide to do the decimal people. If fraction math isn't bad, Then 1 times 9 is 9. 2 times 6 is 12. 3 times 4 is also 12. 3 times 8 is 24. And then at the very end, you add those all up. So 12 and 12 is 24, and another 24 is 48. And finally, we get 57 27ths, which is about 2.1. And what this is measured in is whatever unit we had on our value column. So in this case, we're measuring cents. If you don't like the fraction math, cross out that one, then you would have 1 times 0.33 is 0.33. 2 times 0.22 is 0.44. 3 times 4 divided by 27 is 0.44 again. And 3 times 8, lots of 8. And again, if you sum all of those up, you get about 2.1. So it is impossible for Billy to go to the grocery store and actually spend 2.1 cents. He has to spend a whole number of pennies. But the weighted average is 2.1. If he did this every day for 100 days, he would spend $2.10, probably. This is sort of like the average pain on his wallet or piggy bank or whatever he has. So this is more work, but it's not bad work. All we did was picked some values, did some counting, multiply it across, and then at the very end, add everything up. And this again respects the fact that this situation doesn't happen very much, so we will count it not very much. But we're being fair. We're not counting it equally like the mean would, and we're not totally discarding it as too untypical, too unrepresentative, the way the median might. So the reason people in college care most about this is the same thing happens when you have grades with weights. It's kind of nice to know that Billy spends 2.1 cents on average, but you don't care about Billy. What you care about is something like this. You have different categories. That's just like the outcomes, except that in this situation, it's not like you only have attendance and someone else got lucky in a different way and only had a midterm. These categories, everyone gets all of them. But that's actually not different, because if he went to the grocery store 100 times, he would get all of these too. Sometimes he would get one, sometimes he would get another, but they all happen with this probability. So this is basically the same kind of thing. Throughout the term, every student has all of these things happen. Some days it's an attendance day, some day it's a midterm day, but you get all of them happen. Then we have a number that goes with each thing. And in this situation, the number is what you scored in each category. But these aren't equally weighted. Just like Billy got the blue on his first try more often than the other outcomes, then your grade is mostly your final, less based on midterms and homework, and very least on attendance. So we're going to use the same process to say that all of these count. We're not saying they're equal, that would be median. We're not getting rid of the biggest and smallest, that would be, no, equal would be mean, getting rid of some would be median. We're going to weight them properly. So the one that was the probability, that one we changed into a decimal to multiply with. We didn't want to write this as 33%, or we didn't want to write that as 22%. Does that make sense? So we're going to do the same thing. The one that's the probability, the weights, the things that kind of add up to 100, those are the ones we're going to instead change to be decimals. The percent in the other symbol is a label. Your overall grade has the label of percent. Just like in Billy's problem, the overall thing was cents, so your answer had cents. So we don't have to do any RIPLOP in this column. This percent, we can just pretend it's a label, and it will stick around, and our answer will have percent. But the same game happens. 90 times 0.1 is 0.9. I'm sorry, 9. 80 times 0.2 would be 16. 82 times 0.2 would be 16.4. 84 times 0.2 would be 16.8. 79 times 0.3 would be 23.7. And then when we're done, add them all up. And we get 81.9. And as before, whatever the label on this column was, is what we put on our answer. So overall, this student got an 81.9 in the class. So there's all sorts of real life situations when you hear about this. If you're a farmer, the chance that it will rain today is kind of interesting, but your weighted average of the expected rainfall tells you how much to set your sprinkler system for. And we're okay at making these kinds of decisions intuitively. When I'm going to the airport, I could make categories of how long do I think my plane will be late. A few minutes, up to half an hour, maybe 30 to 60 minutes, more than an hour. And then there might be some number here like how many books I need or how many snacks I need for my kids. And we could figure out what percentages there are for each and work out a weighted average. But no one actually would do that in their head. We just sort of can think about, oh, I have some intuition on how late airplanes are and how many books or snacks I need. and it all kind of works out. The weighted average is sometimes called the expected value. Sometimes that makes sense, like the expected value of the sum of two dice. But it doesn't really make sense to call the grade thing an expected value. It's not expected. That's what somebody really did earn if they got these numbers. So the two phrases sort of fit different situations better, one or the other. But they are exactly the same thing, weighted average and expected value. As always, if we had the factfulness book, we could talk about cool things, but we don't this term. And that's it. That's the very end of Math 25, having new stuff. For homework, then you have two weighted average things, one about inventing a game and one about if you start a food cart business, then about how much can you expect to earn? You're not sure, but there's different chances to earn or lose. And people have started enough food carts that you could do that kind of research. These numbers, by the way, are just fake numbers. You would have to actually find a certain location like Eugene or New York City to get specific numbers you could trust. But you could say, okay, what is likely to happen with my food cart new business if I am a completely average person at running a food cart? Hopefully you are good at running a food cart if you decide to start that business. But pretending you're average, then what would happen? If we go to the random problems, then we have a homework thing, because that's, again, the case you care about the most as a college student, probably. But now we're missing this number. So what do? You can do all the other rows. You can get all these other numbers. And you can say, I want a 77%. So this number, I'm going to put 77. So now I have a subtraction problem. What number will go in this box to make these all add up to 77? So then you get this number. And then this number that has the two question marks, that becomes a division problem. What times this equals that? This divided by that equals that. So I don't want to give it away other than just walking you through it out loud. But try that over the weekend, and I'm sure we will do some of them when I see you next week. So you will be asked on the test the two different things of how to do that, and then as kind of an extra thing, if there were 61 questions on the final, how many questions would you need to get right to get the percent you just found before? As always on a test, if questions are relying on each other and you're not confident of your answer for the previous one, just say that. Say, I got an answer of 20. I don't think that's right. So I'm just, for problem 4, going to say 80% was my answer, and then keep going. And I can test if you're doing the math for this problem right, regardless of what numbers you put in, if you're very clear about what's happening. Same thing if you're trying to do something with whatever, how many feet are in a mile, and you realize for some reason you don't have it in your notes, then just tell me, I forget how many feet are in a mile. Let's say it's 6,000, and keep going. And I can grade your problem and say if you got it right or not based on the math. Who cares about that particular fact for doing the math test? Makes sense? You won't get full credit, but you can get most credit. Again, the random problems are what your practice tests are. So if we go to the playgrounds and gymnasia and Math 25 overall test, since we've now finished everything, you should be able to do a practice test and do all the problems, and they look familiar because they're just the random ones you had in homework all put together. So start doing practice tests. look at the answers, grade your work, and when you've done enough of them, then you can actually take a final. Officially, this is the end of week 8. June starts next week. Amazing. We'll have 1 week that's all review because we've done all the new stuff. And then you'll take your final sometime the week after. These time that our final is 10 a.m. on Tuesday, that's just an LCC procedure. There's nothing saying that Tuesday morning is when you will actually do this. What you will do is, where did I left my thing? You'll tell me you're ready, and then I will go to the bottom and open up the answers and save a PDF file just for me with the answers so I can grade it without having to do all the problems. Then I'll close the answers and print that and send it to you in email. Then you'll take your test and write out the answers, send me a picture of your work, like this student did in the example, and then I can go through and grade your work. And as we talk about here, oral exams are great. They give me feedback that a written exam doesn't. So we'll spend somewhere between 5 and 15 minutes in a one-on-one Zoom or on the phone, and I'll say, let's go back to here. For number 3, that was easy. You didn't bother to show any steps. Can you tell me what you were doing? Or I could say, for number 7, you showed steps nicely. What did you do getting from this step to that step? Or I might even say, somebody else did number 15 wrong. Here's what they did, and I'll show you something on the board. Can you find their mistake? Or something like that. So the oral exam lets me check what's in your brain in a different way than the written test. The more you write down nice steps, the less I have to ask you things because I can see more of what's going on in your brain. But for grading the final, if some of them are very easy, just rip up problems or something, you don't have to write down steps. And if you want to do that early, let me know. If you are ready on Monday or Tuesday of next week to try a final, then you can. You can always try another one if your first one isn't the grade you want. What you don't want to do is wait until Friday, or last week on the 12th, and then take a final unless you're absolutely sure you're going to get this grade you want, because you won't have any time to take another test. So plan on doing lots of practice tests, and if you're doing as well as you think you should, let me know and you can try taking a real one. The score you need going to the achievements to get an A is only a 66. If you get extra stars, remember you get a plus. And when we go down over here, you can get more stars by getting a 70% or an 85% on the final. So doing well on the final is an easy way to get some extra stars to get a plus if you're going for an A+ or a B+. But since the final isn't timed and it's a take-home test, then I can't weight it to that much. So it doesn't really make sense to say even for an A, you need some amazingly high score. So take practice tests until you get 66 or more, or higher than that if you're aiming for those stars. And if you have lots of other things going on in LCC or real life, then you might want to get it done early so you can just be done with Math 25 and focus on the rest of life. And if this next week is really busy, then that's okay. You have some time to take lots of practice tests. Any questions about that? All good. Okay. Any questions on weighted averages? Multiply across, add them up. It's not hard, it's just a new process. You can multiply, you can add. Okay, well, we're done a few minutes early. Thank you. Let's maybe see you Friday at the study session, and otherwise have a good weekend.